Alright, welcome back. Okay, so this is the last part of the carbohydrate notes where I have a lot of information already written down on the page, and we're just going to point out a bunch of stuff and write out a whole bunch of stuff. If you have a whole bunch of colored pens, I highly recommend you have them with you because I'm going to be color coding stuff everywhere. Alright, so let's talk about typical carbohydrates and let's show you some information here. Some of the stuff you've seen before already now. Some things will be some new stuff peppered in, which I'll point out as we hit it. All right, so we've got glucose, which is our blood sugar. It's our main important guy for us. Recognize that we could call it an aldohexose. Yes, you can combine those terms. So it's an aldose, aldehyde, but it's also a 6-carbon piece. So we can say aldohexose. You are allowed to combine those. All right. So point these guys out. You've got, depending on how the printout works, you can kind of already see the numbers there. I'm going to go ahead and write them. 1, 2, 3, 4, 5, and 6. So write out number your carbons. That's going to be important for this. Carbons 2, 3, 4, and 5. Little stars there. They are chiral in the open chain form. Recognize that it is a D sugar. You've got an OH on the right. That is D, hence D glucose. D sugars are the natural sugars. I don't know if I ever said that before. Nature likes D sugars. Nature has evolved to use D sugars preferentially. So D is a natural sugar. You could have the enantiomer, the L sugar, but nature likes D, and that's what we use. And it's what it recognizes. All right. Let's see. Point out other things. I'm just referencing my notes. Let's see. We're going to have to call out that oxygen. I know I'm changing the color coding from the previous page, but we'll go with what I've got on paper so I don't mess myself up. Let's see. So carbon number 5, that's the reference carbon with the OH. He's going to be important when we go to make the ring. And then the oxygen that was the C double bond O is also going to be important. All right, so here we're starting to draw it in a Haworth projection, which is where we just make the ring, but then try to make it obvious that what's up and what's down. You don't have to use wedges and dashes for a Haworth projection. It's just very obvious that a hydrogen or an OH or an atom is straight up or straight down. And that's the terminology we're going to use. It's just an easy way to draw. All right, so what we have is once we turned this molecule, this is still the open chain one, we just kind of flipped it around to try and start making it into a ring to make it easier to look at. So if you like seeing how this happens, you can follow this for a second. The OH on carbon 5 comes over and attacks that carbon, pops this open, and then you still transfer a hydrogen at the same time. It's not explicitly drawn here. But the green one, green oxygen, becomes the new OH. Okay. So, and again, we have this alpha beta stuff going on. So let's actually go ahead and go down here. That oxygen on carbon 5 stayed there. He becomes part of the ring. The oxygen that was the aldehyde now becomes an OH with a transfer of hydrogen. And that can happen one of two ways. The oxygen in the ring stays there, but your OH can either be up, like this guy was, or straight down, drawn that way, and that gives us our alpha versus beta terminology. So alpha here, beta being up there. So alpha D glucopyranose, you can see how we slam all the words together to make a name for it. Glucose, it's pyranose, so it's in the ring form. It's D-glucose, and it's an alpha. So there's a whole bunch of information packed in there. Alpha D-glucopyranose, beta D-glucopyranose. In the alpha beta, the only difference between those two is that carbon there, that carbon number 1, where's that OH? Down is beta, down is alpha, up is beta. Let's see, what else can we talk about? Oh, let's call out anomeric carbon. So carbon number 1 here, that is the anomeric carbon. And go and put your numbers back on if they're hard to tell. They're kind of written there depending on if your printout showed them well, but I'll highlight them for the camera a little easier. There we go. So 1 through 6. Make sure you know the numbering. It actually does matter. So I will ask you about numbering, or expect you to know which carbon I'm talking about. All right. So anomeric carbon, again, is the only carbon that's attached to 2 oxygens. Keep that in mind. It also tends to be carbon number 1. Not always, careful, I'm going to back that up slightly. Tends to be carbon number 1, especially if you're talking glucose. But it's always where the aldehyde was, or where the C double bond O was. That's your anomeric carbon every time. And I'm not going to trick you guys. I'm going to keep stuff drawn pretty much reliably this way, because it's the way we draw carbohydrates. So I'm not going to try and flip the script or flip the picture just to annoy you. Not going to do that. All right. So what else can I say here? Oh, new information down here. There we go. How does the cyclic structure, so these two, if I gave you this without anything else, if you're looking to look at the cyclic structure, how does it reflect D? So the Fisher projection, we know when you have the Fisher drawing, we know it's D just by looking at the reference carbon. What if you're in the cyclic structure? How do you know? Well, it's actually pretty straightforward, and it's actually looking at carbon number 6. Carbon number 6, if it is in an up position, that CH2OH, if it is straight up on the Haworth projection, that signifies D. It's the only time that the CH2OH ends up in D. If you had an L sugar, it would end up being in a down position instead. So it's just a really quick visual check. So terminal carbon is up. That if you're only looking, if you do not have a reference here in the open chain form to reference and know that it's D, if I just gave you this in this picture, it's like, hey, is it D or L? Go look at carbon number 6. That's going to be the trick. So look at carbon 6 in this case, or it's the terminal carbon. It's not always carbon 6, but it's the terminal carbon, CH2OH. If it's up, that is D. One other thing to look at, get my color coding correct. We do have a new functional group that I want to point out, just because it comes in a little bit later, although we don't hit this terribly hard, is a hemiacetal. So a hemiacetal is any group that has this. And R just stands for something, we don't care what it is, carbon-based something. But you have a central carbon that has an OR group, and also has an OH, and then a hydrogen. So as long as you've got a center carbon with 2 oxygens on it, one of those oxygens is an OH, the other is an OR, and then a hydrogen, this will be a hemiacetal. Really what I'm talking about here is surrounding the anomeric carbon. That's it. So highlighted or circling around in purple here, this is your hemiacetal. You have a center carbon, the center carbon has an OH and an OR group, has a hydrogen, and then it has another R group. That's a hemiacetal surrounding that anomeric carbon. It comes a little bit into play later as to if you have one, what does that mean? Is that quickly diagnostic of something? It is. So I bring it up now so that you know the terminology. Hemiacetal. Okay. All right, so that's kind of what we're going to do for most of these. And I'm going to go faster through them, just so feel free to pause me, just to make a point here, but it's a lot of repetition in this case. So if I give you fructose, what can we say about fructose? So fructose is a 5-carbon sugar. It is fruit sugar is probably a good way to remember it. Fructose is here, and I'm sorry, I called it a 5-carbon, it's a 6. It's a ketose. Ketohexose, that's what I was getting wrong. So that's what's different. It's a 6-carbon sugar, but it's a ketone instead of an aldehyde. Same numbering, so from top to the bottom, 1 through 6. We know, in this case, carbons 3, 4, and 5 are our chiral ones. What else do we know? Reference carbon is there. That is to the right. That is D, hence D-fructose. The oxygen that is the carbonyl, in this case a ketone instead of an aldehyde, same idea. That's going to be the key oxygen that we want to pay attention to. So same idea, these guys, we're going to have your ketone and your aldehyde, and your alcohol here. So it's the same scenario. Your OH attacks the C double bond O and pops this open. The only difference is this is happening to a ketone on carbon number 2 instead of an aldehyde. Otherwise, fundamentally the same thing, but it does change your structure a little bit. So what's happening here then is this, get my color coding right. So the OH, or the new OH that we formed, is that one. The oxygen in the ring comes from carbon number 5 there. And numbering wise, watch your numbering here. This is weird since we actually made a 5-membered ring, not a 6. Your numbering, carbon number 1 is the CH2OH here. Then it's 2, 3, 4, 5, and 6. The reason why is because you did a ketone, or you started with a ketone, not an aldehyde. It's the only reason this looks different. Otherwise, very much similar idea. Let's see, so we got numbering there. Let's call out your anomeric carbon. Anomeric carbon, again, in this case is carbon number 2. But your anomeric carbon, again, is the only carbon that's attached to both oxygens, ever. It's the only one in there. That's your anomeric carbon, and it's also the carbon that used to be the C double bond O, whether that's an aldehyde or a ketone. We can say alpha and beta. It's already written for you, but alpha, that OH is down. That's alpha. Beta, that OH is up. Don't pay attention to the CH2OH. It's just the actual OH, that oxygen that used to be the C double bond O. If he's up or down, I'll give you alpha or beta. We can point out, again, same thing as up top. If you look at your terminal CH2OH, carbon 6 again, that, since that's on an up position, that's a D sugar. If we didn't give you any of this to go off of, you could say that's a D sugar by looking at that. And new functional group, very much related to the hemiacetal, is the hemiketal. You can kind of see the terms there. Hemiketal, the only difference is you don't have a hydrogen on the carbon, but otherwise it's really just hinging around that anomeric carbon. You've still got an OH, you've still got an OR, but instead you have a hydrogen, you have 2 R groups. Same idea. It's circling around your anomeric carbon here. Maybe a little hard to circle. That center carbon, you have an OH, you have an OR, and then 2 R groups. That's a hemiketal in this case. All right. I told you that I'd go faster, but lots of little stuff to look at. Let's do it again. Other important sugars. Ribose, he's important. Ribose is a component of RNA. So that's why we want to point him out, because we're going to keep seeing him again. Component of RNA. Ribose is shown here. Recognize that he is a 5-carbon aldose. So pentaldose or aldopentose. There you go. So you combine the terms as needed. All right. I'm not going to label absolutely everything on here again. I just will point out the important parts. Your reference carbon is here. So that OH is to the right. That is D. The oxygen, the aldehyde up here, is your green one. He's the one that's going to get attacked. He's going to also become that alpha or beta OH, so that's why we're tracking him. Again, not going to ask you to do this, but mostly I'll give you this structure or give you one of these and ask you to tell me about it. All right, what can we point out? The oxygen in the ring comes from carbon number 4 here. The OH in green here on carbon number 1, that is your alpha or beta guy. So I guess I will put the numbers on to make this easier. So 5 carbons. Carbon number 1 is here. 2, 3, 4, and then your final carbon kind of always goes straight up. 1, 2, 3, 4, and 5. There we go. So there's your numbering. That's highly important that you keep track of the numbering so that when I'm spouting off carbon 1 and carbon 2, you know what I'm looking at. All right, so this OH from carbon 1 that used to be your ketone, that is down, so that's alpha. And this one's up, that's beta. And you can see the terms there, the labels, the names. We can point out similar things. Let's see, carbon number 5, that CH2OH, is in an up position, so we recognize that, ooh, that's a D sugar if you didn't already know it ahead of time. Now you do. You still have your anomeric carbon. That's this guy, carbon number 1 in this case. Anomeric carbon's also the same carbon that your alpha and beta comes from. Okay. And I'm not going to circle them completely, but I will point out that you do have a hemiacetal on both of these. You can circle them if you like. I spelled that wrong. Acetal. All right, good enough. Okay, so that's ribose. We're going to see him a lot in RNA when we talk about RNA in a couple weeks. Another big one to point out is deoxyribose, DNA, sugar. So, point out your naming here. So I drew just the ring structure of it. So 2-deoxyribose, part of DNA. There we go. Biggest difference here, and let's see what color coding can I use that's not already been used. We'll do bright pink. Biggest difference here is carbon number 2, 2-deoxy. Carbon number 2 does not have an OH compared to regular ribose. All the other pieces are the same. So all that would mean is carbon number 2 up here does not have an OH, it has a hydrogen instead. Otherwise it cyclizes the same, acts the same, does everything else the same. We use the same terminology. So this OH is up, so that's beta. You can circle all the same stuff. It's got an anomeric carbon still. You would just have to make sure to recognize that here, since it doesn't have the OH, that's deoxyribose, hence DNA. Or the sugar important for DNA. Otherwise, everything else is the exact same. Numbering's the same. Carbon 1, 2, 3, 4, and 5. Okay? All right. This video's getting a little long. I'll go ahead and stop here. We'll start on disaccharides on the next one.